We are going to take the ionization energies of the elements as represented here in a periodic table, and we are going to produce tones representing those energies. The way that this app works is each one of these elements in the table is actually a push button, and I can play tones with these push buttons. The settings in this control panel here will determine how those energies will be converted into tones that we can hear. First of all, we're just going to look at a few of the controls for now. See, we have transpose frequency. The frequencies corresponding to these ionization energies are extremely high, so we have to transpose them down to a range that we can hear. So here we're going to transpose it down, in this case, 42 octaves, negative 42. So let's start with hydrogen. If I transpose it 43 octaves down, I get that tone. Or I can go 44 octaves down. I can also transpose it chromatically. As you can see here, I can go up and up again and up again. But normally I set that at 0 and just leave it there, and I only change the octave. Let's go back to 42, and I'm going to show you some of the other controls that we have here. The duration is in seconds, so here we go, 1 second long. Or we could go longer, let's say 2 seconds. And the damping factor controls how quickly the tone decays. 3 is kind of like a nice default. If I set it to something like 10, it's going to decay faster. More of a staccato. If I set it to something really low, like 0.3, then it's going to decay much slower. But it still gets cut off at the end of 2 seconds. Okay, so let's go ahead and listen to some of these. First of all, we are only going to listen to the first ionization energy. So I set this, and it says levels 1. In the case of hydrogen, it only has 1. So there we go. Then we go to helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Now, what happens is, as you start listening to these, you start to notice patterns. Let me go and go through this second row again, but I won't say them. I'll just go ahead and play through them. Kind of a beautiful melody, isn't it? Now, these pitches that we're hearing are determined straight from a calculation based on the actual energy of the element. So we are getting tones that you couldn't necessarily play on a piano. A lot of them would fall in between the keys. So they don't fit our conventional Western musical pitch system. But if you want it to fit, we can enable this. It says quantized pitch. So all these pitches are slid to the nearest note in the chromatic scale. The chromatic scale just means all of the notes that we could play on a piano. That's the best way to explain it quickly. So what I'm going to do is I'm going to go through these again a little more quickly, and I'm going to shorten the duration. I'll go to 0.7 seconds. So let's go ahead and go through this second row again. Now let's go to the next row. Do you hear a connection there? Those two sound kind of similar to each other. Now I'm going to turn off quantization, and I'm just going to go down all of these rows here. The bottom row, we don't have the information for that. So I'm just going to do these 5 rows. Okay, here we go. Now let's go exploring downward, and let's hear the columns. That sounds kind of bluesy. Let's go to the next one. So they're similar. You know, in musical composition, we have what we call theme and variations. And typically, when you introduce some material and then you move on to further material, there's some connection, there's some relationship between the new material and the old. It's the similarity with difference that gives us the sort of the fundamental symmetry that allows our musical compositions to make sense. So there's a lot here that we can work with from a compositional point of view. So as a composer and arranger, I find this really fascinating, and the knowledge that this information comes from the properties of our natural world is really engaging for me. From a purely scientific standpoint, these frequencies that we're hearing are correct. There's a reason why these tones sound the way that they sound. And I'm not a chemist, but I'm giving myself a crash course in chemistry by going through and listening to these tones and relationships, and then digging deeper to understand why the relationships are what they are. Okay, so now we're going to sweep through all the ionization energies from 1 to 108. I want to point out a couple of things. For those of you who are not aware of how this works, this blank space is a placeholder for all of these elements here, the lanthanide series, and then this space here is a placeholder for all of these elements, the actinide series. So we just laid it out that way in order to get everything to fit onto the screen. So as you see, as we work our way down from row to row, the rows get bigger and bigger. There's more and more elements per row. First we only have 2 elements, and then these rows have 8 elements, and then these rows each has 18 elements. These rows each have 32 elements. The data that we have goes all the way up to element 108, so we're going to sweep through those. I do want to point out one thing, and that is as we move through these elements, we find that the pitch interval from note to note, over time they get smaller and smaller. And I think the reason for that is that as we add more and more electrons to the atom, the effect of any one electron makes less and less of a difference in terms of the whole. To illustrate that, I'm going to put up a chart that shows the ionization levels of the first 108 elements. Let's first look at it as a bar chart. So we see that this first row, this is hydrogen and then helium, is just 2 elements in that row. Then we go to the second row and we see basically the same sort of structure, that ascending, but it's broken up into parts. We have 2 going up, then 3 going up, and then 3 going up. Then we go to the next row, it's kind of similar to that second row, 2 going up, 3 going up, 3 going up. But as we see, things are getting more and more scrunched. There's less range. And then we go to the next 2 rows from our table, and we see that there's more elements added. And then the next 2 rows, even more elements added. This piece is duplicated here, except we don't have all the data to fill that out because we only go up to 108. Okay, so I'm going to change the type back to a stair. And so this way it's easier to see the pattern from note to note. And so what we're going to do is we're going to hear all of these in rapid succession, sweeping through from 1 to 108. Okay, here we go. Okay, let's do it again, and I'm going to follow along with my cursor. Okay, so now what we're going to do is we're going to sweep through them again, But this time, instead of having the same time duration for each element, we are now going to have the same time duration for each period. So we're going to take 4 seconds to go through each row of the table. So we're going to spend 2 seconds on hydrogen, 2 seconds on helium. And then we're going to go to the second row and we're going to break that 4-second period up into 8 parts. And then the third row, again, we break it up into 8 parts, 18 parts, 18 parts. So they're going to get faster and faster as we work our way down the table. And here it is, 3 times as fast. And one more time. So far, we've only been listening to the first ionization energy of each one of the elements. Well, hydrogen, because it only has 1 electron, only has 1 ionization energy. But all the elements after hydrogen have multiple electrons and therefore multiple ionization energies. So now we are going to listen to more than one. So what I'm going to do is I'm going to set this to up. So in each case, we're going to go up like a musical scale as we work our way from the lowest energy to the highest energy for each one of the elements. Instead of transposing it down 42 octaves, I'm going to transpose it down 44 octaves. And I'm going to disable this filter so we're no longer limiting ourselves to only the first ionization energy. The other thing is we have now enabled this option here, say element name. So we're going to have my app say the name of each one. So here we go. Here's hydrogen.
Hydrogen. Helium.
So you see we have 2 notes for helium because helium has 2 electrons. Now we go to lithium, which has 3 electrons.
Lithium. Beryllium. Boron.
We're starting to get a lot of range. Those high notes are so high you can barely hear them. I mean, certainly it's difficult to tell what the note is. It's just this really high, sparkly sound. And if we look over here, we see that there's also a frequency filter. See, there's an upper frequency limit and a lower frequency limit. So when you set those, it will filter out any notes that are outside of that range. And this is in hertz or cycles per second. So notice that we are only going up to 5,000 cycles per second. So when I hit carbon, you're not going to hear all 6 notes because some of them are going to go outside of that range. They're going to actually be higher than 5,000.
Carbon.
So we only heard 4 notes. 5 and 6 are outside of that range. Now I could set the octave so that we're 1 octave down. So let's see if we get any more of the notes that way.
Carbon.
Okay, so we got all 6 notes that way. So let's keep it down here at negative 45 octaves. And let's move on to nitrogen.
Nitrogen. Oxygen.
Okay, now oxygen, again, some of the notes aren't playing because they're out of the range. So let's go down another octave.
Oxygen.
Okay, we move on to fluorine.
Fluorine. Neon.
One thing I'm noticing about neon is that those last two notes are much higher than the others. Listen again.
Neon.
So what that means is that those two electrons are so tightly coupled to the nucleus that it takes much more energy to pull those away. Just reviewing what the ionization energies are, I think now that we're hearing multiple notes, we're in a position to understand better what we're actually listening to. Think of it like this. Neon, for example, has 10 electrons. And so that low note, that first low note, represents the energy it takes to pull that first outer electron away from the atom. So it's a low note because it's a low energy, because it doesn't take that much energy, because that electron is in the outer shell and it's farther away from the nucleus, and also in between it and the nucleus there's other electrons, and so the attraction to the nucleus is less. Then as you work your way in and take more and more electrons away from that atom, it requires more and more energy as you work your way in toward the nucleus, and that's why the notes go up. Now with this app we could just as easily listen to it in the other direction. I could change this from up to down. So now let's listen to them going down.
Neon.
Or another thing we could do is go up, down. So it's going to go up and then back down again. And for this, I'm going to change the duration. I'm going to make that half as much. So it's going to be 0.25 seconds on each one. Okay, here we go.
Neon.
Let's make it even faster. 0.1.
Neon. Neon.
Now let's go through and just listen to a bunch of these. So we're sweeping up and down. I've turned off say element name so you can just watch which buttons I'm clicking. We've got ourselves down at minus 45 octaves and 0.1 seconds for each one. So here we go. So as you listen to these, you can hear that we're going up some kind of a scale. They keep getting higher and higher as we go up. But this is not conventional chords and scales. This is just the vibrational relationships that are inherent in the laws of nature. Now let's listen to some of these other ones here. Iron. Cobalt. Nickel. What about iridium? What about uranium? Uranium is here, number 92. Okay, now we're going to compare these in another way. And this will be based on what's called a pitch structure. So a pitch structure is a relative configuration of pitches. And what we want to do is we want to compare the pitch structures for all of these elements. So what we're going to do is we are going to fix that top note as always being the same pitch. So then that way we can compare all the notes below it so that we can hear how the whole structure relates to other structures from other elements. So here's where we do that. Instead of selecting transpose frequency, we select normalized frequency. And the level that we're going to select here, it's already in there, is -1. Okay, the way that this works is just like down here where we look at the levels of which ones we're actually going to play, and that 1 represents the first ionization energy. It's similar in the sense that this number is an index, but because it's negative, it's indexed from the top. -1 represents the highest energy level. That is the innermost, the last electron. If you were to pluck all the electrons away from that atom, this is the last one that you would take. So we're going to set that to something kind of fairly high. Let's say that frequency will be, let's say, 1800 cycles per second. Okay, so, and then I'm going to do just up. And I'm going to let them last a little bit longer. Let's do 0.3 here. Okay, so here we go. Notice that the last note is always the same because I've set that to being this frequency, 1800. Now at this point, I'm going to change the texture to simultaneous. So now we're going to hear all the notes at the same time. This will be a first. Here we go. So you can hear that as these things build and more notes get added to it, those notes are clustering more. They're creating like a thick cloud around that nucleus. And it sounds more and more like a cloud. If we were to go all the way up to, let's say, rhodium. Okay, what about gold? Platinum. Iridium. Now at this point there's so many notes that it's becoming more difficult to distinguish. So why don't we do this? Let's say that we are going to limit ourselves to, let's say, the top 3. So I'm going to go -1, 2, 3. So we're only going to hear the top 3. Iridium. Platinum. Gold. Very similar. I'm not hearing a difference. Let's go back to iron. So I think what's happening is the higher we go, as these electrons are more packed in, they're so densely packed that there's less and less variation because we're adding electrons in the outer shells, but right now we're listening to the innermost electrons. So as we add electrons on the outside, these inner electrons basically can't even hear the outer electrons. So there's less variation. As we work our way down, let's say where there's fewer notes, I think we're going to hear more of a difference. So you can hear that as we go through the table, they're bunching themselves up closer and closer to that top one, and they're changing less and less from one to the other, till finally when we get way up here, 105, 106, 107, we're barely hearing any difference. 108. Now this is interesting because can you hear the octaves? Let's listen to just the top note. And then the one below that. And then the one below that. So 2 and 3 are the same note, whereas 1 is an octave higher. That's not an accident. Do you notice that that identity of notes being octavely related, the ear picks that out. It sounds like it's the same note. It's no accident that in this natural world, this resonance is actually occurring in these ionization energies. And this is one of the reasons why sonification is useful, because anytime you have relative time or relative frequency, anytime you have resonance, which is a very common phenomenon in the physical world, that's exactly the kind of thing that the ear is particularly attuned to. Okay, now we're going to go back from normalized frequency to transposed frequency. We are going to go back to listening to the outer shell electrons, because those are the ones that are more important from the point of view of chemistry. It's those outer electrons that interact with other atoms, and they move from atom to atom. Or when atoms form together in molecules, the electrons traverse around the entire molecule. This app doesn't even deal with molecules. This app is only looking at individual elements. And the other thing that's important to point out is that these ionization energies are something that would normally occur sequentially rather than simultaneously. You're not going to hear 2 different ionization energies at the same time in the same atom. However, if you have a group of atoms together and they're ionized to different levels, then I suppose the simultaneities might actually occur in that case. But just keep that in mind. So what we're doing is we're abstracting. We are now going to listen to just the first 2 ionization energies for each element. In the case of hydrogen, since it only has 1, we'll just hear that 1. In the case of helium, we'll hear both of them. In the case of lithium, we'll only hear the first 2. Okay, here we go. Now, I'm going to transpose these up a little higher so you can hear what's going on here. There are certain relationships that repeat themselves. Frequently, what we have is either octave or something just a little short of an octave or something a little bit more than an octave. For example, in the case of helium here, it's a little more than an octave. It's actually a ninth. Listen to carbon. That's a ninth. Nitrogen, we have the octave. Now we go to fluorine. We have an octave. We have an octave again. Neon, we're just shy of an octave. Now boron and oxygen are a little different because boron, we have a perfect fifth, which is a very consonant interval. And oxygen, a major third. These intervals are very commonly heard in human music. I mean, you know, when we hear sounds in our world and we decide which sounds are pleasant to us, very often we tend to choose sounds that have a resonance. And by resonance, what I'm saying is that the frequency is some simple integer ratio. And the pitch that we hear is the logarithm of the frequency. So just getting into a little bit of the technical details of this. But whether you are up on that or not, you can hear that these intervals, for the most part, sound pretty normal. In fact, what I'm going to do is I'm going to turn on quantization. And with that, I'm going to go through these again. And this really will tune them up to intervals that we are accustomed to hearing in conventional Western music. Now let's work our way down column-wise. Now notice when we get to this last column, this really sounds different from the other columns. Now let's listen to this first column. Now if you notice, all the ones in this first column have a big difference between the low note and the high note. Let's listen again. And the reason for that is all of the ones in the first column are the beginnings of the period in the periodic table. And what that means is that we have just started to fill the next outer shell. So that lone electron in that outer shell has a much lower ionization energy because it's way out there on its own in this new shell. So keep in mind we're only listening to the first two, and there's a big difference between the first one and the second one. Then once we get to the next column, the differences aren't as great. First we'll do this column, and then we'll do this column, so you can hear that there's a bigger difference in that first column than in the second column. And we should expect a small difference in this last column. Notice that the notes are closer together. This outer shell is now full. When you're in the right-hand column, the outer shell is full. So that lone electron is sharing that shell, and so there's less of a difference between the pitch of the first one and the pitch of the second one. All right, let's listen to the first three. Okay, starting with lithium, because lithium is the first one that has 3 electrons. So with lithium, you can really hear that there's a low note, and then there's 2 high notes. And the 2 high notes are close together, and the low note is really far away. Let's go down an octave so we can really hear that better. You see, if I get rid of the first one and just hear 2 and 3, and then we add that first one back in, it's really low. So it has that pattern of all the ones in the left column where the first ionization energy is much lower than the others. Let's go down that whole first column and listen to all of them and verify that the first one is lower, much lower than the next 2. Okay. Now, we do notice, though, that as we work our way down, even though they all have that same pattern, they're closer together than when we're up here. These are much farther apart. These down here are closer together. And that fits the general pattern, because as we fill more electrons in, the difference from one to another becomes less and less. Okay, so I'm going to just step through from lithium up to, let's say, krypton. And we're just going to listen to the first 3 ionization energies. And I'm going to turn off quantization. I usually turn it off because I want to hear the real frequencies that occur in nature. Here we go. you can hear that as we cross the boundaries into different types of elements, the sound changes. Like you notice that whenever we cross from this section into this section, there's always a change. They go down and they start coming back up again. Okay, now let's go back up here and let's listen to the first 4 ionization energies. And I'm going to bump the octave 1 up, starting from beryllium, okay? And I'll go up to, let's say, xenon. And I want to let these ring a little more. So instead of 0.3, I'm going to spend 1 second on each one. Here we go. Now I want to listen to connections between some of these elements. Some of them have similar sounds. For example, we are now down to minus 44 octaves. Let's listen to aluminum and nitrogen. Notice that they're basically kind of the same chord. Okay, so now we're going to sweep through all of the elements for which we have data. That's elements 1 through 108. We're going to go through them really fast. The reason we're doing this is because we want to get a sort of an oral snapshot of the entire sequence. Now this gets a little bit into the fine points of what we call sonification, which is beyond the scope of this particular video. But just one thing I'll say is that by compressing or expanding time to different degrees, we can achieve an analogous effect to visual zoom in and zoom out. So we're going to play through it really fast, which is like zooming out and getting the 3,000 foot overview of the whole thing. Okay, here we go. From 1 to 108. Let's hear that again. Okay, so now let's hear it at half speed. So all the pitches will be an octave lower, the frequencies will be half as much, and it will take twice as long to go through the whole thing. Okay, so now let's hear that backwards. Once again, we're going to do it at half speed, and we're going to go from 108 down to 1. Here we go. There are many more similarities and, in general, relationships between the sounds of different elements in the periodic table. There's a lot of material there, and this is what makes this an interesting area for me as a composer, because I'm kind of just laying out the landscape of this, but actually making music with it opens up tremendous doors of possibilities. And again, I think that this kind of understanding can be useful to scientists because it uses another part of your brain, a different sensory modality that understands the world in a different way, and the ear is a particularly good modality to incorporate because of the way our brain is wired for sound. The auditory nerve coming from the ear splits and goes to all the major centers of the brain. The optic nerve doesn't do that. We are wired for sound in a more comprehensive way than we are for visual. So from a sort of neuroanatomical point of view, it's easy to see why sonification should be useful. Now we're going to go back and focus again on the inner electrons. So now we're back to normalizing the frequency so that the highest energy level will correspond to a frequency of 3,000 cycles per second. And 0.08 seconds for each one. We're going to make this really fast. So we're going to sweep through, again, elements 1 through 108. And what you're going to hear, because you're going to have that same top note every time, but the other ones are going to come up, and closer to it. What this represents is, as we move through the periodic table of the elements, we're adding more and more protons. So there'll be more and more of an attraction to the electrons. So the electrons will more and more bunch themselves up. And we're going to hear the notes that are below that 3,000 gradually move themselves up toward the 3,000. We're going to play that same thing now at half speed. So instead of 3,000, it's going to be 1,500 cycles per second, and it's going to be twice as long on each element. Here we go. And now we're going to do one more thing. We have selected this filter, so we're only going to hear levels -1 through 5. So in other words, we're only going to hear the top 5 energy levels. And we are going to go through and sweep through them very quickly from element 1 to element 108. And by using fewer, by narrowing it down to only 5, it'll be a little bit easier to hear the relationships of these notes up there in the top. And this represents, of course, the inner electrons. And what you'll notice is that not only do they move themselves up and bunch up closer and closer to the top, but they also tend to settle in notes that are octavely related to the top. And so we have this increasing resonance, and it's this interval of an octave that our ear is so tuned to that seems to be a sort of an attractor that is manifest to greater and greater degrees as we work up in the periodic table. Here we go. Now, toward the end, some other things start to happen. I think some other notes start to come in there. The doo-doo-doo-doo-doo, that note comes in, and that's because remember, we're only hearing the top 5. And finally, we're going to hear the same thing, but we've changed a few variables. The texture is now a downward series of notes for each one. We've got the top 4 ionization energies rather than 5. And the duration is going to be real quick as before. We're normalizing the highest ionization energy to 1,500 cycles per second. And this time we are doing elements number 4 through 108, because beryllium number 4 is the first one that has for ionization energies. So we're going to hear a series of downward arpeggios, all coming down from that same top note. And the notes below it are going to start to bunch up closer and closer, and you're going to hear them converge to tones that are octavely related to that top note. Here we go. Now we move from sonification to musification. So we're actually going to hear music. And in this music, some of the elements of the music will be determined by the chemical elements. In this case, we're still doing the ionization energies. Over here, we are quantizing the pitch. But we're going to do more than just hear the resulting tones. What we're going to do this time is we're going to create a musical groove. And the notes played in the groove are going to be determined by the ionization energies of each element. First, we're going to do hydrogen.
1. Hydrogen.
So hydrogen only has that one electron, and the note for the ionization energy is F sharp. This 6 represents the F sharp. So the F sharp is the only note
2.
that we're hearing
Helium.
now. Then we go to the second element, helium, and we're going to get F sharp and E. In this chromatic system, the notes are determined by
3.
numbers.
Lithium.
We go to lithium. The notes are D, C, and G sharp. In this chromatic system, 0 is C, 1 is C sharp, 2 is D, 3 is D sharp,
4. Beryllium.
and so forth. So now we go to beryllium. So here we see for each one of the ionization energies, it's showing us what the notes would be in the chromatic system. So this is C, B, C, and F sharp. And down here, this is an area where we do a sort of a harmonic analysis. And I don't really have time to explain all the details of this. That would be in a future video.
5. Boron.
Boron, the chord that we get is a B flat major 9th chord. Beautiful. So all of the sounds, the percolating arpeggios and everything, that's all an arrangement that I've created. So the only thing that's controlled by the
6.
elements
Carbon.
is the choice of which notes are actually going to be used. So now we go to carbon. And if we were to go through these, you would see eventually that some of the same chords or some of the same bits and pieces of chords come back frequently. So this isn't random. There's a reason why each one of these chords is what it is.
7. Nitrogen. I've taken liberty as an arranger
in deciding which note is going to be the root or the lowest note in the bass, and some other elements of the music that I've decided on. Of course, the drums, the grooves, the choice of all that, those are all decisions that I made artistically.
8. Oxygen.
But the actual notes that are used always come from the elements, the chemical elements. So we hear how the groove changed right there. That was my choice to change that groove. But still, the notes that are being used come from the ionization energies of oxygen.
Nine. Fluorine.
In the case of fluorine and other elements with more electrons than fluorine, I haven't used all of the ionization energies. And this is an example of what I'm talking about when I say musification. I'm making certain choices based on the musicality that I want to create.
10. Neon.
But even in the case where I'm not using all of the ionization energies, I'm still always using the first ones up to a certain point. So I'm always using those outer electrons that have a chemical effect, that have chemical properties. Neon is considered one of the noble gases, and if you listen, it has a kind of a noble sound.
Eleven. Sodium.
I didn't push the button for neon. But anyway, here we go with sodium.
Magnesium.
We're going to end on magnesium. And magnesium is one of my favorites. So the recording that we're listening to moves on to 13, 14, 15. It moves all the way up to 21. And I've been using this track in some of my live performances. So I just play the track that we heard, and having been through these and extensively practicing these and getting to know these harmonies inside out, I'm able to improvise on guitar. And as I develop this, my improvisations are being informed more and more by my understanding of the elements themselves and not just the harmonic properties that are derived from the ionization energies. So this is one of the advantages of musification, is that there are many more dimensions that you can put into the music that can give you other levels or other layers of interpretation of the data. I think the main thing to keep in mind is that it's important to be clear about which attributes have been determined directly from the data and which have been created based on artistic choices. As long as the listener is clear about that, then this approach can be used in a valid way for purely scientific work or for purely artistic work or anything in between. And there's a huge space of possibilities because the variety of mappings, the variety of ways that we can take data and convert it into sound and convert it into music is really huge. So with all those options, I think that there are a lot of opportunities for elucidating the properties of our natural world in a new way and giving ourselves newer and hopefully more profound understandings, and hopefully understandings that will lead us to answers that we might not have gotten otherwise from the scientific standpoint, and also opening up the doors for some new and wonderful music.